In this example, we have a flat plate of mass m located between two equal and opposite jets of liquid. So here's the plate, here's one jet, here's another jet. The jets have some cross-sectional area A, density rho, and a velocity v coming out, and that's the same on the other side. We're told that at time t equals 0, the plate's set into motion, and its initial speed is u naught to the right. So it's initially going off to the right-hand side with the speed of u naught. And after that, its speed is a function of time. The motion is without friction, parallel to the jet axes, and we're asked to find the velocity of the plate and the acceleration of the plate and the maximum displacement of the plate from its original position. So this will be a linear momentum equation problem because we're trying to find the velocity and acceleration of the plate. So its momentum is changing as a function of time. So we might expect linear momentum to be to play an important role in this problem. So if we're going to apply the linear momentum equation, we need to apply it to a control volume. So I'm going to choose a control volume that just cuts across the jet stream coming in and going out. So it'll look something like this. So that's the control volume I'm going to use. And the reason I've chosen that control volume is because we're trying to find the motion of the plate. And so this contains the motion of the plate. And what's causing the plate to move is this jet coming in and then going out vertically. So you can see that the jet has its momentum changing, right? Because it's coming in horizontally and then goes out vertically. So the momentum of that jet is changing, and what's causing that jet momentum to change is the plate exerting a force on it. So the jet exerts an equal and opposite force on the plate. All right, so we also need to have a coordinate system since we're going to be using the linear momentum equation. So I'll put one that's just fixed to the control volume. Call it a little xy, and I'll put a little person there just to indicate that that person is standing. We're standing on the control volume. So it's a non-inertial coordinate system because it's potentially accelerating. So let's write out the linear momentum equation, and it's the x direction that we care about here. Everything's just kind of moving horizontally. So we'll write out the full linear momentum equation in the x direction. So we'll write it all out, and then we'll go ahead and simplify it. Now, because I'm using a coordinate system that's non-inertial, it could be accelerating, I need to put the acceleration term in the linear momentum equation. So this term that I'm writing right now, that's the acceleration of our coordinate system right here with respect to an inertial coordinate system, or like one that's fixed to the ground, and then we multiply it by rho dv, which is like a little bit of mass all inside the control volume. So that's our linear momentum equation in the x direction. So let's start with the first term over here on the left-hand side. So this is the time rate of change of x linear momentum inside our control volume using our coordinate system. So as we stand here, it looks like the plate has zero velocity. Now, certainly if you stand on the ground, it looks like the plate is moving. But if you're standing on the plate, which we are using this coordinate system, then it looks like the plate has zero velocity, zero horizontal velocity. Similarly, the fluid, much of the fluid inside the control volume here also has what looks like zero horizontal velocity as we stand out here. Not everything, but it's pretty close. So this first term is about equal to 0 because ux is about equal to 0 using the chosen coordinate system. Right? It's not 0 because it's steady. This is definitely not a steady problem. Everything is moving. But it's 0 because the x velocity looks like it's 0 as we stand on the control volume. All right, let's do some other easy terms over here. So the body force in the x direction, that'll be 0. We're not told anything about gravity, so we'll just assume that it's not it's not a factor of consideration here. Surface forces in the x direction, that will actually be 0. there are no pressure forces acting on this. We're going to assume that it's atmospheric pressure all the way around this thing. Since these are free jets, it's atmospheric pressure in the jets, so there is no net pressure force. There are no viscous forces acting on the control volume, and no other resultant forces or anything like that. So there are actually no forces, no surface forces acting on that control volume. Let's do this last term. This is the acceleration term. So that's the acceleration of our coordinate system times the mass inside the control volume. So the mass inside the control volume we'll assume is just primarily the mass of the plate. Now there is a little bit of liquid in here, but we're going to neglect the mass of that liquid compared to the mass of the plate. So this can be written then as the acceleration. The acceleration of this coordinate system relative to the ground, or to an inertial coordinate system, is just du dt. So the acceleration is du dt, and then we'll multiply that by the mass in the control volume. And the mass in the control volume we said was just going to be the mass of the plate. So that's approximately equal to du dt times m, where m is the mass of the plate. All right, now let's evaluate the linear momentum flux term. So this is how the rate at which x linear momentum leaves the control volume through the control surface. So let's focus on the left side first. Now we're going to use this coordinate system. So the ux, this is the velocity of the fluid as it's crossing our control surface. Right? It's the velocity in the x direction as we cross the control surface using our coordinate system. So now it's velocity v relative to the ground, and the control volume, or the coordinate system, is moving with a speed u relative to the ground. So the speed of the fluid entering here will just be v minus u using that coordinate system. Okay. So as we stand on here, it looks like the speed coming in is v minus u in the positive x direction. Now you can check this by just looking at some extreme cases. Let's say, for example, u is 0. So if u is 0, then the velocity coming in should be v, which makes sense. Now let's assume that u is equal to v, so that the plate is moving away at the same speed as the jet. Then you'd expect there to be 0 velocity coming in, which works out here as well. Okay, so this is our ux velocity, is v minus u on the left-hand side. Now we need to do the mass flow rate term. So here we have the density times the relative velocity. Now remember, relative velocity is the velocity of the fluid minus the velocity of the control surface. And if I use my blue coordinate system up here, then the velocity of the fluid we just worked out a moment ago is just v minus u in the I hat direction. And then the velocity of the control surface here, if we stand on the control surface, is just going to be 0. So the relative velocity is just v minus u I hat. Okay, so this will be v minus u I hat. And then we dot product it with the area. So the area here will have an area A, magnitude A, and then its unit normal vector, n hat, is pointing in the minus x direction. So this will be a minus a I hat. So this term is our mass flow rate term here. Now we need to do the same thing on the, let me talk next about the streams coming out through the top and the bottom over here. So there, clearly we have some mass flow rate going out, but the x velocity, when we evaluate this integral, the x velocity through the top and the bottom is 0 as we stand on our control volume. So using this coordinate system, the stuff coming out through the top and the bottom looks like it has 0 x velocity, so we don't have to factor that in. That simplifies things quite a bit. If we used a coordinate system fixed to the ground, then we'd have to also take into account the outgoing flows because they would have some x components. So that makes it tougher. So using this blue coordinate system simplifies how we solve this problem because we don't have to worry about the x component of the streams coming out through the top or the bottom here. All right, now let's move on to the right-hand side. Now the velocity of the fluid as it crosses the control surface here using our coordinate system will be the v headed in the minus x direction here, but we have u approaching it, so the velocity that it looks like the fluid crosses our control surface is like a v plus a u. They add together. And again, it's helpful to look at some extreme cases to just double check that you have this right. Let's say u is 0, then it should look like it's coming in with a velocity v, which it does. And if u is approaching v, then they should add together, right? It should look like the fluid's coming at us faster, and indeed we do have it added together. So it looks like it's correct. Okay, so we'll have v plus u, but that's in the minus x direction, so I need to put a minus sign there. Notice that it's pointed in the minus x direction. So this is our ux term again, so this is the yellow term right up here. Now for the mass flow rate term, we'll have the density times the velocity, we just said was v plus u, in the I hat direction. By the way, I just noticed I made a little mistake up here that, wow, I just deleted everything. Let me fix that back up again. This is v minus u. I put the I hat in the wrong spot. There, fixed. Okay, so we have v plus, I'm back down here now. So the relative velocity will be just the velocity of the fluid minus the velocity of the control surface. But again, the velocity of the fluid is v plus u, and as we stand on the control volume, the surface speed, the control surface speed is 0. So it'll still just be a v plus u I hat, and it's in a minus I hat direction because it's pointed to the left. So that's where the minus comes from. And then we have to dot product that with the area. The normal vector for the area, n hat, is in the positive I direction, so it's just going to be a I hat. So this is our green mass flow rate term that's given right here. Okay, so now let's go ahead and simplify this out. We'll have on the left-hand side, we have these terms. So let's expand those out. So the first one will be a minus rho v minus u squared times a. And the next one is a plus rho v plus u squared times a. And on the right-hand side, we have a minus du dt times m. All right, I think I've got that all correct so far. So now we can go ahead and simplify. Let me expand out the left-hand side. So there we'll have a minus rho times v squared minus 2v times u plus u squared times a plus rho v squared plus 2v times u plus u squared times a is equal to minus du dt times m. And I wanted to expand it out because you see this term, let me double check. Oops, no, that's not correct. This term, the v squareds cancel out, the u squareds will cancel out, and then the 2 times v times u, those terms will actually add together. So this will be a 4 times rho v u times a is equal to minus du dt times m. And then you see that we have a differential equation here that we can solve. So what we're trying to do is we're trying to get the velocity of the plate initially here, as well as the acceleration of the plate. So we're working on the velocity right now. So if I just rearrange that equation that I have here, I'll have du all over u is equal to minus 4 times v, 4 times rho times v times a divided by m, and then a dt. Let me just double check that I did all that correctly. Yeah, that looks good. And then I can integrate both sides with respect to u on the left-hand side. So it starts at some initial velocity, u naught, we were told. And then it goes to some final velocity. And on the right-hand side, at t is equal to 0, is the lower part of the integral, and then out to some arbitrary t. The left-hand side will integrate to be a natural log term. So it'll be natural log of u over u naught. The right-hand side, you can see all these terms, the minus 4 rho v a all over m, those are all constants, so they come outside the integral. And we're left with t on that side. So the velocity, we can take the exponential of both sides, and the velocity will be u naught times the exponential of minus 4 rho v a all over m times t. So that's our velocity of the plate as a function of time. And then if we want the acceleration of the plate, that'll just be du dt. So that'll just be a minus 4 rho v u naught a over m times exponential of the same thing that we had in the box above it. So it should look like that. Let me just double check I have the sign correct. Yeah, that looks good. Okay. So there's the velocity and there's the acceleration. The last part of the problem, let me go back up here, is what's the maximum displacement of the plate from its original position? So we're trying to find the position as a function of time, and then we'll just take a look at it for a long period of time. So to find the position, we know that the position is just related to the velocity by taking dx dt is equal to the velocity, right? So we can substitute in for our velocity now that we know it, and then integrate both sides on this. Okay, so I'm just solving this differential equation. We're going to go from x equals 0 to its final position. I'll just call it xf for final. And then the right-hand side, t goes from 0 to some very large t value. So I'll put, let me change in my limits. On the upper limit, I'm just going to call it some arbitrary x, and then I'll call it some arbitrary t there. And then we'll take the limit as t goes to infinity to get the final position. So the left-hand side is just an x. The right-hand side, we'll have, let's see, it'll be a u naught all over the minus 4 rho va over m times the exponential of minus 4 rho va over m times t. But then I have to also plug in a value of 0 here when I evaluate that integral, and that'll come out to be a 1. So x, I'll carry this negative sign through the square brackets. All right, I think I'm in pretty good shape there. So that's our position as a function of time. And if I want to find the final position, I'll just take the limit of x as t goes to infinity. So just after a long period of time. And if I do that, you can see as t goes to infinity, this will go to a 0, and I'm just left with the 1. So the limit as t goes to infinity is just this. So this is our final position after some long period of time. All right, hopefully all that makes sense to you. So just to kind of recap again what we've done here, it's a linear momentum equation problem because we're trying to find the velocity and acceleration. The acceleration is really kind of the tip-off for the linear momentum equation. So we applied the linear momentum equation to a control volume surrounding the plate, and one of the key parts of this problem is to put the coordinate system on the control volume. It just makes the analysis much easier. Some other little parts to highlight. When we evaluate the time rate of change of linear momentum in the control volume, that's 0 because the ux is 0 using that coordinate system. When you evaluate the linear momentum flux term, you just have to be careful of the velocities using that coordinate system. You have to view what these velocities are coming in as you sit on the coordinate system. So these yellow ones are a little tricky. So you have to be careful with that. I don't think there are any big issues with body and surface forces here or the acceleration term. Once you have that, this is the fluid mechanics part of the problem. And then the rest of this, all down here, is just math. All of this is math. And in fact, even this part, finding the final position, is the math part as well. So the fluid mechanics part is really all contained in this part right up in here. All right, hopefully that all makes sense to you. We'll go ahead and end the example there.